Learning objectives. At the end of this topic, you will be able to collect data and classify them as primary data and secondary data, represent data in frequency distribution tables and in graphs, bar graphs, histogram, and frequency polygons, calculate measures of central tendency, mean, median, and mode. Introduction. Every day, we know about a lot of information in the form of facts, numerical figures, tables, graphs, etc. in newspapers, televisions, magazines, and other means of communication. These facts or figures collected with a definite purpose are called data. The extraction of meaningful information is studied in a branch of mathematics called statistics. Analysis of data can give us different kinds of information. Collection of data not only helps us to keep track of current happenings and trends, but also helps us to predict what might happen in the future. When the information is collected by the investigator himself or herself with a definite objective in her or his mind, the data obtained is called primary data. When the information is gathered from a source which already had the information stored, the data obtained is called secondary data. Presentation of data. Consider this example. 100 plants each were planted in 100 schools during one Mahotsav. After 1 month, the number of plants that survived were recorded as given below. The data in this form is called raw data. By looking at this form, can you find the highest and the lowest number of plants that survived? No. It's difficult to find out the highest and lowest number of plants that survived from this large amount of raw data. Consider the number of plants that survived in the first 10 schools alone. Now can you find the highest and lowest number of plants that survived? Yes, we can arrange the numbers in ascending or descending order and find out the highest and lowest number of plants that survived. The highest number is 98. And the lowest number is 28. The difference of the highest and lowest values in the data is called the range of the data. So, the range in this case is 98 minus 28, which is equal to 70. Now consider the number of plants that survived in the first 30 schools. Here, presentation of data in ascending or descending order can be quite time-consuming since the number of observations in this experiment is large. Hence, we find the frequency. The number of schools where a certain number of plants survived is called the frequency of those number of plants survived. For instance, 3 schools have 65 plants that survived. So, the frequency of 65 plants that survived is 3. To make the data more easily understandable, we write it in a table. This table is called an ungrouped frequency distribution table or simply a frequency distribution table. Now let's consider the whole data. To present such a large amount of data, we condense it into groups like 20 to 29, 30 to 39, and so on, up to 90 to 99, since our data is from 23 to 98. These groupings are called classes or class intervals, and their size is called the class size or class width, which is 10 in this case. In each of these classes, the least number is called the lower class limit and the greatest number is called the upper class limit. Example, in 20 to 29, 20 is the lower class limit and 29 is the upper class limit. Using tally marks, the raw data can be condensed into a tabular form. For 20 to 29 plants that survived, the frequency is 3. So the tally marks is drawn like this. For 30 to 39 plants that survived, frequency is 14. Hence, the tally marks are drawn like this. Similarly, for the other values, the tally marks are drawn accordingly. Presenting data in this form simplifies and condenses data and enables us to observe certain important features at a glance. This is called a grouped frequency distribution table. Here we can easily observe that 50% or more plants survived in 8 plus 18 plus 10 plus 23 plus 12, which is equal to 71 schools. We observe that the classes in the table above are non-overlapping. Note that we could have made more classes of shorter size or fewer classes of larger size too. For instance, the intervals could have been 22 to 26, 27 to 31, and so on. So, there is no hard and fast rule about this, except that the classes should not overlap. Graphical representation of data. It is said that one picture is better than 1,000 words. Usually, comparison among individual items are best shown by means of graphs. This type of representation then becomes easier to understand than the actual data. In this chapter, we shall study about 3 types of graphical representation of data: bar graphs, histograms of uniform width and varying width, and frequency polygons. Bar graphs. Bar graph is a pictorial representation of data in which usually bars of uniform width are drawn with equal spacing between them on one axis, say the x-axis, depicting the variable. The values of the variable are shown on the other axis, say the y-axis, and the heights of the bars depend on the values of the variable. Observe the bar graph given below and answer the following questions. A. How many students watch TV for 12 to 14 hours? B. How many hours did the maximum number of students watch TV? Solution. Note that the variable here is the number of hours, and the value of the variable is the number of students. So, 30 students watch TV for 12 to 14 hours, and the maximum number of students watch TV for 9 to 11 hours. Let's now construct a bar graph for the data below. The students of a particular school have collected 20,000 rupees for Teachers' Day celebration. They had planned the following expenditures under various heads. Solution. We draw the bar graph of this data in the following steps. We represent the heads, variable, on the horizontal axis, choosing any scale, since the width of the bar is not important. But for clarity, we take equal widths for all bars and maintain equal gaps in between. Let one head be represented by 1 unit. We represent the expenditure value on the vertical axis. Since the maximum expenditure is 5,000 rupees, we can choose the scale as 1 unit is equal to 1,000 rupees. To represent our first head, that is memento, we draw a rectangular bar with width 1 unit and height 4,000 units. Similarly, other heads are represented leaving a gap of 1 unit in between 2 consecutive bars. The bar graph for the given data is drawn like this. Here, you can easily visualize the relative characteristics of the data at a glance. Example, the expenditure on food is more than double that of the costume expenses. Therefore, in some ways, it serves as a better representation of data than the tabular form. Histograms. This is a form of representation like the bar graph, but it's used for continuous class intervals. For example, consider the frequency distribution table given below, representing the heights of 30 people in a locality. Let us represent the data given graphically, as shown. We represent the heights on the horizontal axis on a suitable scale. We can choose the scale as 1 unit is equal to 10 centimeters. Also, since the first class interval is starting from 139.5 centimeters and not 0, we show it on the graph by making a kink or a break on the axis. We represent the number of people, frequency, on the vertical axis on a suitable scale. Since the maximum frequency is 9, we need to choose the scale to accommodate this maximum frequency. We now draw rectangular bars of width equal to the class size and lengths according to the frequencies of the corresponding class intervals. For example, the rectangle for the class interval 139.5 to 149.5 will be of width 1 unit and length 6 units. In this way, we obtain the graph for the given frequency distribution table. Observe that since there are no gaps in between consecutive rectangles, the resultant graph appears like a solid figure. This is called a histogram, which is a graphical representation of a grouped frequency distribution with continuous classes. Also, unlike a bar graph, the width of the bar plays a significant role in its construction. Here, in fact, areas of the rectangles erected are proportional to the corresponding frequencies. However, since the widths of the rectangles are all equal, the lengths of the rectangles are proportional to the frequencies. Now consider a different situation. A teacher wanted to analyze the performance of 60 students in a mathematics test. So she formed the following table. A histogram for this table was prepared. Carefully examine this graphical representation. Do you think that it correctly represents the data? No, the graph is giving us a misleading picture. As we mentioned earlier, the areas of the rectangles are proportional to the frequencies in a histogram. Earlier, this problem did not arise because the widths of all the rectangles were equal. But here, since the widths of the rectangles are varying, the histogram above does not give the correct picture. For example, it shows a greater frequency in the interval 70.5 to 100.5 than in 60.5 to 70.5, which is not the case. So we need to make certain modification in the lengths of the rectangles so that the areas are again proportional to the frequencies. The steps to be followed are as given below. 1. Select a class interval with a minimum class size. In this example, the minimum class size is 10. 2. The lengths of the rectangles are then modified to be proportionate to the class size 10. For instance, when the class size is 30, the length of the rectangle is 29. So when the class size is 10, the length of the rectangle will be 29 by 30 into 10, which is equal to 9.67. After the modifications, we get the following table. Since we have calculated these lengths for an interval of 10 marks in each case, we may call these lengths as proportion of students per 10 marks interval. So, the correct histogram with varying width is frequency polygons. There is yet another visual way of representing quantitative data and its frequencies. That is a polygon. To see what we mean, consider the histogram drawn for heights of 30 people. Let's join the midpoints of the upper sides of the adjacent rectangles of this histogram by means of line segments. Let's call these midpoints as B, C, D, E, F, and G. When joined by line segments, we obtain the figure B, C, D, E, F, G. To complete the polygon, we assume there is a class interval with frequency 0 before 139.5 to 149.5 and 1 after 189.5 to 199.5. And their midpoints are A and H respectively. A, B, C, D, E, F, G, H is the frequency polygon corresponding to the data. Although there exists no class preceding the lowest class and no class succeeding the highest class, addition of the two class intervals with zero frequency enables us to make the area of the frequency polygon the same as the area of the histogram. Frequency polygons can also be drawn independently without drawing histograms. For this, we require the midpoints of the class intervals used in this data. These midpoints of the class intervals are called class marks. To find the class mark of a class interval, we find the sum of the upper limit and the lower limit of a class and divide it by 2. Thus, class mark is equal to upper limit plus lower limit by 2. Let's consider the following example. Here is a table showing the charges of a courier company for packages with different weights. Let's draw a frequency polygon for this data without constructing a histogram. Solution. Since we want to draw a frequency polygon without a histogram, let's find class marks of the classes given. For class 0 to 20, the upper limit is 20 and the lower limit is 0. So, the class mark is equal to 20 plus 0 by 2, which is equal to 10. For class 20 to 40, the upper limit is 40 and the lower limit is 20. So, the class mark is equal to 40 plus 20 by 2, which is equal to 30. Continuing in the same manner, we find the class marks of the other classes as well. We can now draw a frequency polygon by plotting the weights along the horizontal axis and the rates along the vertical axis. Then plot the points B, C, D, E, and F. Join the plotted points by the line segments. Now we draw the histogram for the given data to gain better understanding. Is this a complete frequency polygon? In order to complete this polygon, we need to join it to the x-axis. But how do we complete this polygon when there is no class preceding the first class? For this, consider an imaginary class interval of -20 to 0 before the first class interval given in the table. Also consider the class interval of 100 and 120 after the last class interval given in the table. Join the midpoint of the class interval, -20 to 0, that is -10 on the x-axis, to the beginning of the frequency polygon. Join the midpoint of the class interval, 100 to 120, that is 110 on the x-axis, at the end of the frequency polygon. This completes the required frequency polygon, that is A, B, C, D, E, F, G. Frequency polygons are used when the data is continuous and very large. It's very useful for comparing two different sets of data of the same nature. For example, comparing the performance of two different sections of the same class. Measures of central tendency. The three measures of central tendency are mean, median, and mode. Now let's discuss about the mean or average. The mean or average of a number of observations is the sum of the values of all the observations divided by the total number of observations. It's denoted by the symbol x bar, read as x bar. As we've studied earlier, mean is equal to sum of all the observations divided by total number of observations. Let us consider the following example. 5 people were asked about the time in a week they spend in doing social work in their community. They said 15, 10, 13, 20, and 25 hours respectively. Let's use a variable xi to denote the ith observation. In this case, I can take the values from 1 to 5. So our first observation is x1, second observation is x2, and so on till x5. So x1 is equal to 15, x2 is equal to 10, x3 is equal to 13, x4 is equal to 20, and x5 is equal to 25. Therefore, mean is calculated as. So the mean time spent by these people in doing social work is 16.6 hours in a week. Now, in case we are finding the mean time spent by 30 people in doing social work, writing x1 plus x2 plus x3 up to x30, it would be a tedious job. We use the Greek symbol sigma for summation. Instead of writing x1 plus x2 plus x3 and up to x30, we write sigma I is equal to 1 to 30. xi, which is read as sum of xi as I varies from 1 to 30. So, x bar is equal to sigma I is equal to 1 to 30. xi by 30. Similarly, for n observations, x bar is equal to sigma I is equal to 1 to n xi by n. Here also finding the sum of all the observations and then dividing by the total number of observations is tedious. Hence we use frequency of a particular observation to make our calculation easier. We find the sum of observations as f1 x1 plus f2 x2 plus so on, that is sigma I is equal to 1 to n fi xi is equal to f1 x1 plus f2 x2 plus so on, and the total number of observations as f1 plus f2 plus f3 plus so on, that is sigma I is equal to 1 to n fi is equal to f1 plus f2 plus f3 plus so on. In brief, we write it as x bar is equal to sigma I is equal to 1 to n fi xi divided by sigma I is equal to 1 to n fi. This formula can be used for ungrouped frequency distribution. Median. The median is the value of the given number of observations, which divides it into exactly 2 parts. So when the data is arranged in ascending or descending order, the median of ungrouped data is calculated as follows. When the number of observations, n, is odd, the median is the value of n plus 1 by 2 observation. For example, if n is equal to 13, the value of 13 plus 1 by 2th observation, that is, the 7th observation, will be the median as shown in the figure. When the number of observations n is even, the median is the mean of n by 2th and the n by 2 plus 1th observations. For example, if n is equal to 16, the mean of the values of 16 by 2th and the 16 by 2 plus 1th observations, that is, the mean of the values of the 8th and 9th observations, will be the median as shown in the figure. Let us consider an example. The heights of 9 students of a class are given. We have to find the median. First of all, we arrange the data in ascending order as follows. Since the number of students is 9, an odd number, we find out the mean by finding the height of n plus 1 by 2th observation, that is, 9 plus 1 by 2, that is the 5th student, which is 149 centimeters. So, the median, that is, the median height, is 149 centimeters. Let's consider another example. The points scored by a basketball team in a series of matches are given. We have to find the median. Arranging the points scored by the team in ascending order, we get, there are 16 terms, so there are 2 middle terms, that is 16 by 2, and 16 by 2 plus 1, that is the 8th and the 9th terms. So the median is the mean of the values of 8th and 9th terms. That is, median is equal to 10 plus 14 by 2, which is equal to 12. So the median point scored by the basketball team is 12. Mode. The mode is that value of the observation which occurs most frequently. That is, an observation with maximum frequency is called the mode. Let us see the following example. Find the mode of the following marks out of 10, obtained by 20 students. We arrange this data in the following form. Here, 7 occurs most frequently, that is 4 times. So the mode is 7. The ready-made garment and shoe industries make great use of this measure of central tendency. Using the knowledge of mode, these industries decide which size of the product should be produced in large numbers. Summary. Let's summarize the topic. Facts or figures collected with a definite purpose are called data. Statistics is the area of study dealing with the presentation, analysis, and interpretation of data. The raw data can be organized and represented in frequency distribution tables. The data can be presented graphically in the form of bar graphs, histograms, and frequency polygons. There are 3 measures of central tendency for ungrouped data. They are mean, median, mode. Mean is found by adding all the values of the observations and dividing it by the total number of observations. Median is the value of the middlemost observation. Mode is the most frequently occurring observation.